So my talk will have two parts. In the first part, I try to introduce a large collection of extreme problems, which basically says that in combinatorics, there's lots of important problems can be reformulated as inequalities of certain polynomials. And in the second part, I'm gonna treat our own problems and give a detailed proof. And this joint work with my two PhD students, Hao Chen and Yupeng Lin, also with my collaborator Wei Fan from Duke University. So let's begin with this Hilbert's tense problem. In this famous problem, he's if we are given a positive integer n and also a polynomial with integer as the coefficients with n variables, can we find a general algorithm which determine so you are giving me this polynomial and I want to ask return the answer yes or no if there is an integer solution to this integer polynomial. And turns out we know the answer is no. There's no general algorithm or there's no systematic method can tell you this answer the question correctly. And this is a big breakthrough by Matthias Kuvish in the 70s. So I mean, and today's talk basically what we do is provide you some new understanding of this type of result in combinatorics in some setting of so-called the graphic homomorphisms. So when I prepared this talk, actually I searched online and actually find some more connection between the Matthias Kuvish and combinatorics, and he actually published a paper in Journal of Graph Theory. And what he did there is actually he finds some statements of the four-color theorems using some probabilistic setting. But it's off topic, so I just want to quickly mention this. Okay, back to our problem. There is, important notion in graph theory, also important for our talk. So it's the so-called the graph homomorphism. So we are giving two graphs, H and G, and a homomorphism from H to G is defined to be a mapping from the vertex set of H to the vertex of G, such that it preserves the edges, in the sense that if you have UV edge in H, then if you look at the images, FU and FV is also an edge of G. Now this notion actually is very helping. It's helpful in various aspects I'm going to mention later. But for a moment, let's look at the second notation. It's basically tell us, this is notation basically tell us counting the number of graph homomorphisms. But for our needs, we need to define this on the weighted graph. So GW denotes edge-weighted graph with edge with W, where this W assign edges by some real numbers. It actually, in many situations of talk, it can be negative. Then this weighted homomorphism number from H to this GW actually defines the following summation, which call it hom HGW. This summation go over all possible homomorphism from H to G, and for each of these homomorphism, we look at the following contribution of this phi. That is the product of every edges ij, and for this edge ij, I look at the corresponding width of the new edge in your graph G. So if we're talking the naive case, then so say G is a simple graph, then W is just a 0-1 mapping from the edges. If the edge is in G, then we map 1, otherwise we map 0, right? Then G is a simple graph, then this notion actually denotes the number of graph homomorphisms from H to G. Okay, then we denote this homomorphism density. That is the notion we just defined, divide by the total number of possible mappings we can have. That is Vg raised to the power of Vh. Okay, so it has a sense of, it has a probabilistic sense here. So if we choose a mapping randomly, this notion denotes the probability you got this random mapping is homomorphism. There's some, I want to mention a useful property here. So if I've given two graphs, H1 and H2, I'd use this notion H1, H2 means the vertex disjoint union of those two graphs. Then, if we look at the homomorphism density of TH1GW times the homomorphism density H2, then this actually equal to the homomorphism density of H1, H2 I just defined here. This actually is helping because it basically turns any product of this density into just a linear term. So if you basically can, if you have given some polynomials of many those densities, if you use this operation, so basically all of these things becomes a linear, it's accumulated here as a linear term. Okay, I will come back to this point later. So the central talk, the topic I want to bring into this talk is that there are many, many important problems in extreme combinatorics. Actually, we do study algebraic inequality between homomorphisms. I can give several examples. But before those examples, I want to denote another important notion here. It's called the quantum graph. A quantum graph is just a form of linear combinations of graphs. For instance, here, if we are given a finite many graphs H1 to HT, and we're also given some coefficients C1 to CT, then I put it together as a linear coefficient, the summation of Ci times Hi, then this thing is my quantum graph. Okay? Once we have this quantum graph, I can define the homomorphism density for quantum graphs. So TFGW is simply just the linear combination of these corresponding homomorphism densities for these graphs Hi. Okay? Now, if we are using this property here, then it will be easy for us to say that actually any polynomial of homomorphism densities can be expressed as a linear combination. So any polynomial of this density can be viewed as the homomorphism density of your quantum graph. Just take example here. For example, you are given this t to the cube, and this h is a triangle, and plus say matching size 2. And this can be, by using the previous one, this is equal to 3 triangle here, G plus T matching. I mean, even here, I can put half. Half, the whole thing becomes half 3 disjoint triangle plus a matching G. And this is our quantum graph G. Quantum graph H, F. So any sort of this polynomial can be reduced a problem for this quantum density, this quantum graph problem. There's a famous question by Lowas. So when he developed this theory of graph limits, he raised many fundamental problems. One of the problems is asking, can we characterize all these quantum graphs which satisfy that his homomorphism density, which is always non-negative for all possible weighted graph? And the point here is that here GW, this width function W, can take values in the negatives. And later on, he has some specific, like he also proposed some specific solution to this. But Okay, I'm going to talk this in minutes. But before that, I want to give you a few examples, which, I mean, those are problems in extreme complexity we care about, and this actually fit in this general framework. The first one is the so-called Sidorenko conjectures. Was there some equivalent form which asked earlier by Ehrlich and Simonovich? But in those days, I think we're more kind of interested in this version provided by Sidorenko. So he's asking for any bipartite graph H. And we look at every graph, host graph G. So G usually, you think this G is a big graph with number of vertices tending to infinity. And we want to look at the homomorphism density of H in G. And this basically, we are counting the number of copies of H in G. And we want to know how many copies of G. And the Sidorenko conjecture that the minimum number of copies of H is achieved by a random graph with the same edge density that we care about here. So the notion TK2G means the edge density of G. And this term appear on the right-hand side actually counts the number of copies of H in a random graph GMP where P equal to this TK2. Okay? So he's saying, like, basically, if you look at your favorite bipartite graph, say C4, a cycle of length 4, and you count anything in a big graph, and you know that the minimum number of copy of C4 in your big graph actually is given by the random graph. And there are many progress going on. I mean, for this Sidorenko conjecture, for example, we know it's true for all even cycles. It's also, this conjecture also holds for all complete bipartite graph and so on. But in general, this is still open. Maybe some people actually believe this is false. I mean, but we are not able to find the correct construction here. Well, here I want to mention that actually this conjecture can be reformalized as the language of this quantum graph as follows. So recall this product thing. So we can use this K2 raised to EH denotes the disjoint union of a matching of size EH. Then if we do this and we define the quantum graph to be FH, that is denoted by the H minus K2 raised to the EH, then this question is basically exactly equivalent to asking if for this specific quantum graph, TFG positive or not for all graph G here. But there's others conjectures can be using stated in this language. Another conjecture is called this KNIS conjecture. The underlying idea is basically want to generalize this Sidorenko's conjecture to general graphs. Sidorenko conjecture only states for bipartite graphs, and basically, and the form suggests like the only obstacle which may make this conjecture wrong is when your graph G is a non-bipartite graph. Therefore, therefore, this group of researchers, Koyakawa, Nago, Rado, and Schack, they propose a notion of a smaller family called this Lodi dense family. So we say an n-vertex graph is called a Lodi dense if you look at any subset with positive proportion number of vertices, say at least rho times n vertices, then any such subset should contain many, many edges, and at least half d times x squared many edges. So any low d dense graph actually is far away from being bipartite. Therefore, we can ask for any graph H, and is that true that when we count the copy of H in this specific family of G, this the number of copy of H is still minimized by the random graph like GMP, where P is given by this the H density we care about here. There are some easy properties we can read from the definitions. First of all, any graph H satisfying the significant conjecture will automatically satisfy this K and S conjecture. Because after all, here we're asking for a weaker property. But nowadays, people do know actually the graph H satisfies this K and S conjecture actually is broader than the Sri-Lanka conjecture. For example, any complete multi-parted graph satisfies the K and S. Also, all these autocycles actually satisfy the K and S conjecture. But as the conjecture this holds for all graph H, that is still widely open. I mentioned one last example is called the positive graph conjecture. It's also due to Lowas. So Lowas is interested in characterizing all simple graph H such that when we look at this, the homomorphism density of H in any weighted graph, this density is non-negative. And he actually has a nice guess. So he's conjecturing a graph is positive, meaning satisfies this conjecture, if and only if it is symmetric. So what is symmetric? So if H satisfies this, the structure of H must be looked at this. We have some subset of verses, and this is an independent set. And then the rest of verses can be partitioned into two parts, A and B. And between A and B, there's no edge, and A and B are isomorphic to each other. Okay. Now, if your graph is looked like this, totally symmetric in the sense, then when we can rewrite this homomorphism density as many sum of squares, because it's sum of squares. Therefore, we know this. No matter what it is that the weight is positive or negative, the sum of squares always tell us this is positive. And I mean that it's still open, but in the previous several years, I think that we have some progress in basically. I mean, there's some weak evidence tell us this is true. For example, I think there's recent paper showing that if any positive graph, it has a vertex whose degree is even, because, well, but in general, it's all of those conjectures are quite open. Okay, so now let's go back to the the first problem raised by Lowas. So he's asking which quantum graphs F can satisfy that the TFGW is always positive for any weighted graph. And he actually proposed some certificate for this non-negativity. And he's proposing the following. So if F is such a quantum graph, then there must are two quantum graphs, G and H, such that we can express our F as F times 1 plus G, and this is equal to H. And where G and H can be wrote as the summation of squares of some other quantum graphs. So what he's suggesting is basically like any such satisfying F must can be rewrite as a fraction function. So any such a F can be rewritten as H over 1 plus G, where H is is some summation of some squares, and the G is also some summation of squares. Okay. Obviously, if you have such form, then you can prove this non-negativity. In 2011, there was a breakthrough by Hatami and Nori. They basically answer this question negatively. So they show that if we are given any quantum graph, your favorite quantum graph, and this consists of the following information: an integer k, and a finite many graphs h1 to hk, and your integers a1 to ak. And we are not able to answer the question like this homomorphism density of this quantum graph is always positive or not. There's no general algorithm or systematic method you can answer the yes or no question correctly. Well, I mean, in their setting, so basically they can answer the question for all weighted graph where the weight taking value between the value actually is in a closed interval between 0 and 1. Okay, so the important point here is that they are only restricted themselves in this range. For example, they cannot extend the weights to be negative. But nevertheless, they answer the most important cases of this lowest problem. But in last year, there's a new paper by Blackerman and Raymond and Wei Fan. So they basically completely answered the lowest question. And they show that if we consider a family of weighted graph where this family contains all simple graph, this sentence basically say take weights in 0, 1. So basically, this is a family of simple graph. As long as the width, the family you consider contains simple graphs, then the answer will be undecidability. The answer will be there's no general solution, general algorithm you can provide to answer this question correctly. So again, we are given any quantum graph, and you ask if, so you also give me your weighted graph from your family G, and you also ask me if this homomorphism density is positive or not, then I should tell you that there's no general solution can tell you this correctly. Okay. Well, for us, we want to basically look at this further, and we want to generalize those settings from graphs to digraphs. There's a natural candidate for digraph that is the tournament. So a tournament is just an orientation of complete graph where for every edge I decide the direction either from your vertex A to B or from B to A. And then with this notion, you can generalize those previous definition correspondingly. For example, we can define this homomorphism in digraph. Let's say from a digraph F to a tournament T will be also a mapping from the vertex to the vertex, which it preserves the die edges, right? Whenever you see an edge, direct edge from U to V, and the image FV is also direct edge. If this mapping preserves this property, then that's we call it this homomorphism. Also, we can define the homomorphism density. That is the total number of the homomorphism divided by the total number of mappings we may find here. So this important thing is this T is always is a real number between 0 and 1. Okay. So why we actually care about this, like why we care about this, the homomorphism densities in digraph, was there are many aspects. There are many generalizations of classical problem in graph theory. Actually, people asking digraph. For example, there are some natural Ramsey version in digraph there also this famous problem of Airy-Channel. People also find it's actually the original Airy-Channel conjecture is equivalent to some setting in tournaments and so on. Another thing is, so it's not clear what is the problem, and we should ask. And there are also some obvious obstacles because the tournaments are asymmetric, unlike the graph case. Okay, so we look at this new problem where we are given a quantum digraph, meaning we have many finite digraphs d1 to dk, and we are also given some real number c1 to ck, and you take this formal, the formal linear combination of these digraphs, denote this is G, and we want to know if the quantum density of this, if the homomorphism density of this quantum digraph is always positive when we look at the host tournament T. So we would like to answer this question correctly. So if you give me your tournament T, and I will ask you if this is positive or negative. The main result we have is, again, this problem is undecidable. So there's no algorithm that could always give you the correct answer, yes or no. So again, it's, in other words, it's undecidable if a quantum digraph is always negative, non-negative or not. So, I mean, in some sense, it's, you expect this answer to be undecidable, but the proof actually requires, it's much less non-trivial here. So the general idea behind our proof is basically want to reduce our solution to this Mattia-Kirchhoff solution. And here there's several equivalent formula provided by his solution, but here the one we want to reduce our problem to is this version. So we are given an integer coefficient polynomial, and we want to answer the question if there is an integer solution such that this p is negative, and the answer is, again, is non-decidable. But then in their paper, Blackman, Raymond, and Wei, they basically show that there's an increment formula. Instead of you looking for solution in Z, well, you can looking for solution in the inverse of Z, okay? And again, if you're looking your solution in the inverse of Z, and you want to say if you have have an instance such that your integer polynomial is negative, for this new problem, the answer is still undecidable. Okay, there's some nice trick, but it's not very hard to actually to get this. But then they actually move one step further. They say that if you give me a polynomial, I can make a new polynomial called a p-bar. P-bar will have double number of variables. Originally you have s variables, but now in this new polynomial p-bar you have 2s. Okay, and we even have they give this precise formula. The nice thing is now the question if you have a solution in the inverse of integers is equivalent to the solution of in some specific range I'm going to specify later, and this is actually important for our proof. But right now, let's hide this. If you have some special pairs such that this becomes your solution to this new polynomial, okay? And the important thing is basically using this two-step reduction, they reduce this this infinity domain problem to some finite domain problem. Okay, earlier you look at your solution in like all possible integers, which is infinite many. But now they basically reduce the problem where we only need to care about a finite range. And that's kind of important. Okay. So now I explain what is the range R. So this is the R states in this two-dimensional Euclidean space. So I actually look at this. And we have a curve. So this is x equal to 1. This is a straight line. And this stands for this y equals x squared. But then you look at all possible integral points, say half and 1/3, 1/4, and going on. This is our range R. Okay. But for the moment, it's not clear like why those like arbitrarily given polynomial are related to our problem, right? So we have to give some combinatorial meaning. I mean, this is we want to. So the easy way to do this, actually, the efficient way to do this is basically replace the variable xi by some careful chosen digraph homomorphism density. And then we plug in, and then in this way, actually, the polynomial p has some meaning in combinatorics. Okay, this is very rough, but I'm gonna explain in more details in next slides. And maybe I skip. Okay, so so the challenge is basically to tear what is the right digraph homomorphism density we need to put in xi, and it contains two aspects. First, what is this hi? What is this small digraph we're counting, and what is the host tournament t we're gonna choose? Okay, so and most of our proof is basically is giving construction of those two kinds of sequence. So first we need to define what is the digraph we are counting. That's we call it a necklace. So the necklace is basically formed by again some special rooted digraph, where a rooted digraph means a digraph with two special vertices called the roots. And we arrange those rooted digraph in a fashion of cycle. Okay, like this is a cycle of length 4, but you can have longer cycles, for example, 6 cycle, 8 cycle. Then you put any two adjacent vertices a rooted digraph, and you put the same rooted digraph between any two consecutive graphs. And in this way, we form this called the necklace. So necklace will be a digraph which is has no rooted vertices. So we are actually counting the copy of the necklace in some special tournaments, and we plug in those counts, those homomorphism density as your variable. And when we plug in certain, I mean, some polynomial give to me and multiply by something. Notice that with the question we care about is we want to know if there's a solution which makes this negative or not, right? If we multiply some positive term here, it does not matter. It will not change your answer. But when we multiply this, actually it makes sense to view this whole thing as the homomorphism density of some quantum digraph. Okay, so the thing is, this is not very important, but when we do this, it has a certain right meaning for us. Okay, you can interpret this as a real homomorphism density of some quantum digraph. Now I'm telling you what is the right homomorphism density we're going to put here. This is actually a fraction. This is a fraction of one divided by another, and then we're counting the necklace of C8 divided by the square of the necklace of C4, and this is proper chosen y square, but I'll tell you later. That's the x, and this y is also something similar. So when we do this replacement and into this polynomial, the important thing is we need to show that now this is the vector actually we care about, but it's important to us to prove that all those vectors actually stay in this range. Only that we can use the one lemma provided by this Blackman, Raymond, and Weiss their lemma. So this is basically the range given by the vectors. Actually, we actually take here, and we want to show is basically all of those. This range is contained in some Cartesian product of the star. Okay. So we want to show that if you give me your particular integers R1, Rs, and I want to show that this vector is achievable by our homomorphism density. The second one is easy, but mainly we want to show this item 1. So at this point, probably it's fair to say that the major part of proof is we're looking for a constructive proof. Okay? We want to show that all of those particular vectors are achievable. So now I'm gonna sketch the proof. So it contains two parts. We want to construct a sequence of necklace. We want to construct a sequence of big host autonomous Tn. So that we can show like the corresponding x and y is approaching this 1 over Ri and 1 over Ri squared. And each of this construction actually there's a long way to go. So actually I want to just briefly. For the necklace, there are 3 steps. The first step is to construct a random tournament such that it satisfies the 3 propositions, and those propositions are I will not explain why they are needed, but mainly because for the counting purpose. And the second step in constructing this necklace is to turn this random tournament into a looted tournament. And the picture is like this. We have the random constructor F0, and we put 2 roots, and we basically divide F0 into 2 parts. And then in the first part, we put in a direct path, say from Zi to this vertex and to Wi. In the second part, we do the opposite. So it will be W towards this vertex and towards Zi. So there are 2 different lengths of paths of length 2, and here we actually like distinguish these 2 paths. And the third step is basically duplicates this processing. So we do this once, and then we do this like symmetrically. Why we need this? Because by doing this, when we count any copies of this, the symmetric ones in your tournaments, it will be symmetric between x and y, right? So you call this x and y, and you want to map your two roots to your choosing versus x and y in your tournaments, and because this graph is symmetric, therefore it does not matter you switch the rules x and y. This is kind of important because once you have this, you can basically interpret the counts as a weighted graph. So you care about you basically care about this, and you treat this as the interest of a matrix, but because they are symmetric, so therefore you can interpret your matrix as a weighted graph. And then when we're counting this necklace in your T, this can be treated as you're counting the number of copies of cycles in this new defined weighted graph. Therefore, we can, people understand how to count the number of cycles because it's just using the eigenvalues. That's for the construction of necklace, and the second construction is for the tournaments. And it's also kind of complicated because those host tournaments must be designed according to this previous necklace, like this Fi. So there are quite many steps. In the very end, so we have some tournament TI, but the very end step is basically to zoom all those tournament TI to one huge tournament we call the T star. It's like this. Then we have a lemma, say we can understand this for the last whole tournaments as some weird distributed like matchings. And in the end, we need to use a famous construction by Noga alone. It's this famous pseudo-random triangle free graph. There are some other family graphs we can use, but we need to choose one. And so the main purpose is to say, like, when we look at the eigenvalues of graph, the largest eigenvalue dominates other eigenvalues, and this is the main purpose we need to use. So after all of this, so basically we can calculate the homomorphicity for this necklace well. So we can use those eigenvalues. So you can express the x variable as the summation of the eigenvalues, but because the largest eigenvalue lambda 1 dominates others, so basically this is really counting the eigenvalues lambda 1. And because we make choice of in the denominator to be square, so a nice way is that everything cancels out and you only have this 1 over I left. And for the y variable, you could do the similar things. What you left with is 1 over I squared. So when k going to infinity, and you see this two variable actually is approaching to the integral point actually we want here. I think that's all the talk I want to share. Thank you.
All right, thanks for the talk. Any questions? No question? Okay, if not, then let's thank our.
Thank you.